Okay, hello everyone. Welcome to the Chilean Probability Seminar. Today we have the pleasure to have with us Paul Maurer. Paul is a PhD student at the Callisto team in INRIA, and he will talk us about the strong convergence of a numerical scheme for jam-driven SDEs. Paul, you have the microphone.
Thank you very much, Hector, and thank you for inviting me to your seminar and letting me talk. So yeah, indeed, I will talk about a numerical scheme, which is rather close to the Euler-Maruyama, but for jump-driven SDEs, and especially time-inhomogeneous jump SDEs. So this is a joint work with Mireille Bossy that maybe some of you know already here, which is in the audience. Okay, so jump-driven SDEs. So here is typically the class of SDE we will work with. So we have a drift. We may have a diffusion part, but I just omitted it for this talk because it's already too long for the formulas. And we have this jump coefficient C, which have 3 parameters. So it can depend on the times, on the state of the process, and of the size of the jumps. And then we have N, which is what we call the random Poisson measure, which basically is a random measure that give information about when does the jump occur and how big they are, the size they have. This kind of model is very interesting because it allows a lot of flexibility. In particular, it's non-Gaussian, so it can be good if you want to model like heavy tails phenomenon. One can think of some models in biology to describe the population dynamics. Some insect, for example, that can show some non-Gaussian regimes and different time regimes too. It could also be useful in finance because it's allowed to price to some pricing over a very big range of maturities and strikes. And one of the main motivation we had for this work was to try to represent the angle dynamics of non-spherical particles inside a turbulent flow, which is typically some kind of process that is non-Gaussian and shows some transition regime coming from something with heavy tails to something more Gaussian with different time regimes too. So yeah, this is for the applications that are possible. And our goal is to construct some numerical algorithm, so xn here, to simulate and approximate the process x. We will derive what we call the probabilistic strong error with respect to the LP norm for this type of algorithm. So let's talk a little bit about the Euler-Maruyama scheme. So if we start from a standard diffusion process, so here x, with a drift b and diffusion coefficient sigma, then we can the easiest way to approximate the process x is to define the Euler-Maruyama scheme. So where we just use the increment of the time and the increment of the process w. So of course, this is a very easy scheme. It's very easy to implement. And the reason for that is because we have a way to simulate this increment of 2 Brownian motions because we know how to simulate Gaussian random variables. So in the case we will see later, we'll talk about Lévy process. And in this case, it will be a little bit more complicated to simulate these increments. Okay, so to start to generalize a little bit this, we can think about what are the main properties of Brownian motion. So it has independent increments, stationary, and Gaussian. So first, if we remove the Gaussianity, we get what we call Lévy process. So there are processes which has independent and stationary increments, but not Gaussian. And it comes out that if you remove the Gaussianity of the process, you also remove the continuity of the trajectories. And you get some process which is not continuous, but only CAD lag, so right continuous with left limits. And those are Lévy process. So for this case, you can still define the Euler-Maruyama scheme, but you might have some problem into simulating the increments of it. And in some situation, it is possible, and we have some algorithm to simulate the law of this. It's, for example, possible if you take the well-known case of alpha-stable process. So alpha-stable process, there are a class of Lévy process that shows very heavy tails and that has infinite variance. So they are rather useful, usually. But here we will focus on process that has a finite variance, and we will see how we can get some processes that are rather close to alpha-stable process in terms of behavior and of PDF, but still has finite variance. And it comes out that if you take a pure jump Lévy process with finite variance, you can get from the Lévy-Ito decomposition this representation here in terms of random Poisson measure. So a random measure that account for the time of the jumps and the size of the jumps. And this representation will be very useful to generalize a little bit more the equation we have here. So just before doing this, I will go to a third class of generalization, which is when we remove the stationarity condition. And then we get what is sometimes called additive process. So there are processes with only independent increments, and they are not stationary in time anymore. And this case is pretty similar to Lévy process. You can still define Euler scheme. It's getting trickier and trickier to simulate the increments, of course. And the main difference in the Lévy-Ito decomposition is the measure nu, which is, so nu here is the expectation of the random Poisson measure n. So it's a deterministic measure. And in this case of additive process, it will depend on the time. In case of Lévy process, it's homogeneous in time. So based on this Lévy-Ito representation, we can do something a little bit more tricky about the noise of the process X. And instead of just putting something which is a multiplicative noise, again, the increment of a stochastic process, we can do something like this. So it was the type of equation I talked about in the introduction. This is double integral in time and in space, and with this coefficient C that can allow more complex interaction between the state of the process and the size of the jumps. And then you get back this random Poisson measure. So this case is way more complicated than the others because here you don't really have an underlying process properly, and you can't really base the scheme on the increments of something. So in this case, the Euler-Maruyama scheme doesn't even make any sense. You can't really give some sense to it. And you have to rely on other techniques to try to approximate this integral, this stochastic integral. Of course, there is one case where it's the same as before, is if the coefficient C is just multiplicative in X and in Z. So if it can be written as sigma of X times f of Z. And in this case, you can get an underlying process and you can just get back to the previous slides. But here we will consider the more general case. So I think a natural question that arises is how to simulate, how to approximate this type of stochastic Poisson integrals here. And the answer for this is splitting them. So splitting them is like you take a threshold epsilon positive, and then you separate this stochastic Poisson integral into two terms. The first term is the jumps that are in absolute value bigger than epsilon, and the second one is the jumps that are smaller than epsilon. And why is it interesting to do this? Well, because the big jump integral can be actually very easy to simulate directly. We can get direct numerical techniques to simulate it, while the small jumps, basically it concentrates all the problems. And we will try to find a way to approximate it properly. So I will talk about on the easy part, let's say the big jumps. So the big jumps, it can actually be represented as a finite random sum. So this one here, minus some deterministic integral, which is related to the compensation we used. So the main term is the first one, is this random sum. So I will describe, of course, what are these n, t, and z. So n here is just a time-inhomogeneous Poisson process. So it has some intensity function lambda, which you can compute. And the t epsilon are just the jump times of this Poisson process. And then the z epsilon, they are basically the random variables that account for the sizes of the jumps. And it comes out that we can find the conditional distribution with respect to the jump times. So, okay, it might appear a little bit complicated because it depends on the time, it's not IID. But okay, let's say if we take something rather simple, if the dependence in time of the Lévy measure is just multiplicative, if nu can be written as phi of t times nu, for example, then in this case, it's a little bit simpler because you can see that if you take this quotient here, the phi t will just simplify and you get some distribution that will not depend on t anymore. So in this case, you can still have IID random variables for the jump sizes, and it's a little bit easier to simulate. So, okay, if we sum up what things we have to do to generate this large jump integral, well, we have to do three things. The first one is generating the Poisson process and epsilon. So this can be done by different techniques. So it's not homogeneous, but if your intensity function lambda is bounded, you can use some thinning method. So thinning method, it's some kind of acceptance rejectance algorithm, and it's rather fast to do. And if not, you can still rely on some like brutal inversion method that still work. Then you have to generate the jump sizes. And for this, okay, this might be the tricky part in the general case, but it comes out that for most of the Lévy measures that are interesting for the applications, for example, the truncated stable process that we will see just after, this is not too difficult, and we can have some algorithm to simulate this. It's way easier to simulate this than to simulate the whole stochastic integral, of course. And we can find some inversion algorithm or acceptance rejection algorithm for this, the epsilon in most of cases. And finally, of course, we have to compute this deterministic integral. And well, this really depends on the structure of f and of nu. And if they have almost the same structure, it will be easy to do it analytically. For example, if f is polynomial and if nu is something like 1 over z at the power something, then you can compute it, there is no problem. And of course, in the difficult cases, you can still rely on some numerical integration techniques, but then the scheme will be heavier and heavier, of course. So here I will take a rather simple example where everything is going well. So just before I talked about the alpha stable process. What? Yes?
Hello, I have a question.
Sure.
At this point, you're not speaking about the Euler scheme, or already you're in the setting of the Euler scheme?
It's some kind of introduction to my scheme, so you can understand it better. Okay, so for now, I didn't define any scheme yet.
Yeah, because now by the moment you're simulating the big jumps, but I'm not saying how you're going to use them in the dynamics of the SDE, let's say. Probably
exactly.
You will not fix the position of X probably and use. Okay, but you will.
Exactly. Yes. Exactly. It's totally this. So I give you a way to simulate in general this kind of noise structure, and then I will apply it to derive a scheme including the dynamic of the process.
Okay. Thank you.
So yes. So yes, I was talking about this truncated stable process. So they are very similar to stable process. They share the same structure of Lévy measure, which is this z at the power -1 plus alpha, where alpha is between 0 and 2. But the difference between stable process is here we force a jump to be bounded, because for a standard stable process, the jumps can be as big as you want. And this is what is creating this infinite variance that we have. And if you truncate the jumps and if you force them, at least in expectation, to be smaller than some constant, here 1, then you get a moment of order every p for this process, and you still keep a part of the behavior of the stable process. So in this case is very useful for many models, especially in physics, because in physics, usually the process, they have a variance. They don't have infinite variance, but they can still show the heavy tails. So we use them a lot. And in this case, it's not too bad. So here I choose to use a multiplicative time dependence, so it's not too complicated. And it's bounded, so you can use thinning method to generate the Poisson process. And for the jump sizes, they are IID because the time dependence is multiplicative. And it comes out that you can actually compute their quantile function. And it's something very explicit. So it's very straightforward to simulate. You just take a uniform random variable, you apply Q epsilon, and you get your simulation of Z in this case. And finally, the deterministic integral, the correction here is just 0 because we have an odd function. So in this case, everything goes pretty well. Okay, so now that I talked a lot about the big jumps, I will talk a little bit about how to deal with the small ones. So for the small ones, it's more complicated because we cannot really have this finite random sum representation, because actually it would be more like an infinite random sum with jumps that can be arbitrarily small. And of course, you cannot really like generate an infinite sum of very small things on a computer. It doesn't really make sense. So you have to find a technique to deal with this. So one first strategy will be maybe just to ignore them, to say we take epsilon as small as we want, and we only simulate the jumps bigger than epsilon, and we totally ignore the small ones. So this does work, but actually it leads to some rate of convergence that are maybe not that satisfying. And it comes out that there is another way that works a little bit better to deal with small jumps. And I will give an heuristic for this. So here I showed two things. On the left in blue, you have the trajectories of a truncated stable process, but with a very, very low truncature. We took some like 0.01. So basically it's account for the small jumps of this process, the jumps smaller than this epsilon. And on the right in green, you have trajectories of a Brownian motion that has been renormalized to get the same variance. And you can see that they're pretty similar, they're pretty close. Of course, this wouldn't work if you have big jumps, because you will see the jumps in the blue ones. But here the jumps are so small that they almost look like a trajectory of a Gaussian process. And then it gives a heuristic that instead of just neglecting the small jumps, maybe you can just approximate it by Gaussian variables, actually. And this was the idea of Asmussen and Rosinski. So this idea is not new at all. It's maybe 20 years old already. And they applied it in the case of Lévy process. But here we want to extend it to like a general stochastic Poisson integral. And also more important, we want to derive some quantification in LP norm of the error that is made in this approximation. So maybe just one remark is how did I do to generate this Lévy process here? So the truncated stable process, when alpha is between 0 and 1, it's a very specific case where there exists actually a direct numerical algorithm to simulate the small jumps. And this has been made by Dacios, Lim, and Chu. But this is a very heavy algorithm, computationally very intensive, and it only works in this case. But at least it was enough to try to show my point in this specific case. So a little bit more formally, we will try to approximate. So it's IL of f, so it should be S and not R, sorry. It's the small jump integral. And what we say is the law of this small jump integral is exactly the same, almost the same as a standard Gaussian variable that has been renormalized to fit the same variance. So you can actually compute easily the variance of a random Poisson integral. There is some kind of formula which gives you it. So it poses no problem. So to quantify the errors that we are making by this approximation, and to be able to quantify with the LP norm, we will use some kind of weaker form of the LP norm, which is the Wasserstein distance of order P. So for those who don't know it, it's like the infimum on all the couplings between two distributions L1 and L2 of the LP norm of this random variable x1, x1, and x2 that are following. That has for marginals L1 and L2. So this is close to the LP norm, but it's a little bit weaker. And actually it comes out that you can always find optimal couplings. So two random variables, x1 and x2, that will satisfy this infimum. And this will be very helpful to construct an optimal coupling of our scheme with the actual process. But we will see this a little bit later. So I will give one proposition to estimate the errors that we are making. And it is the following. So here we take a deterministic function f, which is non-zero on some ball of radius, let's say 1. So it's a ball in dimension 1. It's nothing in higher dimensions. And we ask for p+2 moment condition on f with respect to the Lévy measure. And if this is satisfied, then we can quantify the Wasserstein distance between the low of the actual small jumps and a Gaussian variable centered with the same variance. And this is quantified by this horrible term here. But the only important thing is system will go to 0 when epsilon goes to 0, at least if we assume a sufficient condition on f, which is not that restrictive. So just some words on the proof of this proposition. So everything is based on some quantification of the central limit theorem in Wasserstein distance, which has been proved by Bobkov in 2018. It was a conjecture from Emmanuel Rio 10 years ago. And this result says that you all know that the central limit theorem is that the distribution of the sum of independent random variable will converge to a Gaussian distribution. And you can actually quantify this convergence in the Wasserstein distance. And what will comes out of this is the p+2 moments of the random variables that you have. So if you are able to control the p+2 moment of them, then you are able to control the error that is made between the approximation between this sum and this Gaussian. And something important is this result even holds if the random variable are not IID. And this is important because in our case, if you want to like discretize our stochastic integral, we get independent random variables, but they are not IID because they are inhomogeneous in time. So thankfully, this result still work with this. And by doing this time discretization, we can get this xj. And then we only need to know that the moment of order p+2 is bounded by something interesting. And for this, we may use Kunita inequalities that I will talk a little bit later. But basically, it's a form of PDG inequality for a jump process. Okay, so now that we have every ingredient, I can talk about what we call the epsilon Euler-Maruyama scheme. So how to incorporate the dynamic of the process with all this. So the method is the following. So we do something that is very close to the Euler-Maruyama for the drift part. It's exactly the same actually. And then we add, in green, we have everything that comes from the big jumps. So this deterministic integral, this finite random sum. And finally, in red, we have the approximation of the small jumps. So the psi A are Gaussian random variable, centered one. And the red term is only the variance of the process at time ta. So you can see that maybe one difficulty in the most difficult cases if these two integrals cannot be pre-computed before doing the scheme, you might have to do numerical integration at each step. But in the cases we are using, we can actually pre-compute them and it's no big deal. So the main theorem of this work was to give some convergence results for this algorithm in the LP norm to the process X. And we have to note that we have two parameters in this scheme. We have the number n of discretization steps, and we have this threshold epsilon. So of course, every result that we have will depend on these two parameters. And we will try to kind of make them match to get something interesting. So let's talk about the hypothesis we need. So the first ones are very natural. We have something very smooth. It's the drift is Lipschitz. The jump coefficient is Lipschitz in space. With respect to time and jump, it's a little bit more complicated. We only require some integrability condition on this LC. So the integrability condition is given by this like function psi p here, depending on LC, on C0, and on P. And basically, if this function is only integrable only in L1, then the process admits moments. Unfortunately, this is not exactly enough to derive a bound for this strong error. We need a little bit more integrability, and this is why we need this zeta here between 0 and 1. We need it to derive some local error in the proof. It's for some kind of technical arguments. And if zeta is equal to 1, then you have something in L2. And this gives you the best result that you can hope. You cannot hope for something better if zeta is bigger than 1. So finally, we have some condition which is a bit more specific to our approximation. We call it the Asmussen-Rosinski approximation condition. So first, there is this p+2 moment hypothesis, which is necessary to derive the proposition that I showed just before. So to quantify the error that is made between the approximation of the small jumps by random Gaussian variables. And finally, we have this coupling approximation. And this is required because we only have this quantification in a weak way, in Wasserstein distance. So to actually get something in a strong way, we need some optimal coupling. And for this, we require basically to have some density with respect to the Lebesgue measure for the small jump integral, which is usually the case for the interesting situation. And we require that the Lévy measure is infinite near 0. But of course, if it's finite, then you don't really need to do any approximation because you can, everything is simulated, can be simulated straightforwardly. So we have some corollary, no, we have the main theorem here. So in the main theorem, we have to construct this optimal coupling. So it will be a version of the scheme that we called X hat that is required to have the same law of our scheme. So in law, it will be exactly the same. But it's constructed in a way that we can derive something from the Wasserstein approximation. We first show that this version of the scheme has finite moments and they are uniformly bounded with respect to epsilon. And then we derive our rate of convergence, which is composed into two terms. So you have one term in the number n of discretization steps. So when the psi p is integrable enough, the zeta will be equal to 1. And in this case, this 2 zeta and 1 plus zeta is just equal to 1. So you have some 1 over p here that is left. And then you have this contribution on epsilon, which come from the use of the proposition that I showed just before. And this contribution is a little bit awful, but once again, it will go to 0 when epsilon goes to 0, at least at fixed n. And we will see that under a little bit more conditions on the jump coefficient, we can get something way better than this. So it's our corollary here. If we assume that the C is sublinear with respect to Z, so of course this includes every type of multiplicative noise, for example. If you have a Lévy process, then this will be satisfied for sure. And in this case, you can get something way more explicit for this contribution in epsilon. It will be just epsilon times square root of n. So if you want to derive something good, you have to choose epsilon small enough. So if you choose it smaller than n at the power minus 1 over 2 plus 1 over p, then you can actually make it match the first rate. When zeta equal to 1, you have n at the power minus 1 over p. So if you know a little bit about the strong rate of convergence for SDE driven by Brownian motion, you know that it should not depend on the p. Usually it's just minus 1 over 2 for every p. But here in the jump case, we have this p that appear, and it's not coming from the approximations that we are making. It's really coming from the lack of continuity of the trajectories. And we will see how it appears a little bit later. So to do the proof of this theorem, so I won't go into too many details, but I will just give a sketch of the idea we are using. And the first idea is we use a pivot term, which is kind of a continuous version of what will be an Euler scheme if it would exist. So we call it the Euler piano scheme. So it's the SDE where you just freeze the coefficients. So of course you can't really simulate this, but it really helps us as a pivot term. And as a first proposition, we prove the strong error for this tiled x. And we only have the first term in n. So we can see that the p is already appearing here, even we didn't do any approximation of the jumps. So the proof of this proposition is rather standard. It's relying on some Grunwald arguments, but it has some specificities due to the non-continuous trajectories. And the most specificity is the type of inequality we are using. So of course, we need some inequalities to estimate LP moments of stochastic Poisson integral. And they actually are martingales. So one may think about why not using the Burkholder-Davis-Condy inequality. But the problem in the non-continuous part is the quadratic variations that appear here in the BDG inequality. If M is continuous, it is the same as the predictable quadratic variation, which is the thing you can calculate. So it's the thing that gives you this squared thing and p over 2 in the outside. But the thing is, for not continuous process, this is not equal. And you can't really do anything with this quadratic variation. So you have to rely on other techniques. And one inequality that does exist for already some time, it has been stated by Kunita. And it's an inequality it's a BDG, but specific for stochastic Poisson integrals. And actually, the first term is very, very similar to BDG. You have this f squared and this p/2 in the outside, but you have an additional term here, which causes a problem. And this is because of this additional term that we have the 1/p in the result. Because here you have f at the power p, but you have nothing outside. You have nothing to compensate outside. And this will create a problem. And this term is really unavoidable for p bigger than 2. So I will go just about how do we prove this proposition. And for this, I just recall how do we do in the Brownian case with Lipschitz coefficient. So it's a very easy proof. Maybe you all know it by heart, I don't know. I still go through it very fast. So the idea is we set this E of t, which is the supremum of this strong error. And we want to derive something with a Grunwald argument. So if we use the definition of the SDE of x and tide x, we can apply Minkowski inequality, and in the Brownian case, we can apply the BDG inequality, get something like this. This is 2, and then this is 1/2. And we can take advantage of the Lipschitz property of the coefficients. Maybe I forgot to explain this notation, like this weird inequality notation. It just means that it's up to a constant that does not depend on p and t, but nothing more than this. I didn't want to add constant in this because it's already too long. So you get this, and if you get this, you almost have your Grunwald argument, but you need some pivot term to conclude. And the pivot term you use will make appear some local error term, which is the one in red, and the one in green is just actually your function e, so it will be used in the Grunwald lemma. So then to conclude, if you want to use Grunwald lemma, you just have to bound the red terms, the local error terms, and in the classical case, it's very easy to do because you have like a s minus eta of s is smaller than 1/n. And you can apply again the Minkowski and BDG inequality on the red terms to finally get something in n at the power minus 1/2. And the 1/2 really come from this 1/2 here. So in the jump case, it's a little bit more tricky, even if it works the same. So here we need to use the Kunita inequality instead of BDG. So it will be the terms in pink here. And there is, of course, these two terms, the one which is similar to BDG, and the one which causes some problems because we have this p and this 1/p. And here it's also a little bit more technical because we have this psi p, which is not bounded in time. It's only integrable, a little bit more than integrable. So it's a little bit more difficult to bound the local error, but we can do it with some Holder inequalities and integration by party. It works rather well. And in this Holder inequality, we need this supplementary integrability in time. So this zeta that appear in the theorem. And then the rate that we get has this problem that it depends on 1/p here. So this 1/p is giving the 1/p in the end that we have. So I don't detail the rest of the proof. It's rather standard. And I just wanted to insist on the singularity of the jump case. So finally, I can go to the proof of theorem 1. So to prove the theorem 1, we need to do 3 things. So the first thing is maybe the most difficult. We have to construct a version of the scheme that will live on the same probability space as x and satisfies some optimal coupling property for the Wasserstein distance of order p. So this we will detail a little bit more. And then the other steps are rather standard. We need to find the uniform bound in epsilon for x. So this is once again done by a Grunwald argument. Actually, with the construction we have some discrete martingales. We can use the discrete BDG inequality for the discrete martingale, so it works rather well. And to derive the upper bound for the LP norm of the difference between the Euler piano scheme, our pivot, and the version of the scheme that we just constructed, it's also done with the Grunwald argument. And also thanks to the proposition 1 that we can actually use with this version of the scheme. So this gives us the delta epsilon term. So a little bit about the construction of this version of the scheme. So let's just fix the step I, and we are interested in trying to transport the distribution of this random variable. And we want to do it for every x, because then we will apply it to our process at some state xt I-1. So to be able to do this, we need some optimal transport, but with measurability with respect to the parameter x. Because if not, we can never apply it to some random variable after. And we want this optimal transport to satisfy, of course, an optimal property for the Wasserstein P distance, which will allow us to use our bound that we have already. So to do this, we used some results from Joachim von Bona, Hélène Guérin, and Sylvie Mellard that ensure us that so if we take Qi, which is law of the process of the scheme, sorry, at the state Ti-1, then we can find a measurable application Ti such that for almost Qix, we have this optimal property between Ti, which is our Gaussian variable, and Yi, which is the small drop integral that we had before. And if this is satisfied for Qi almost every x, then it will work for us because we only need to apply this when the small x is equal to big X at the time Ti-1. So this is enough for us. And the measurability is very important because then we can define our scheme with this Ti, which now is nothing that a random variable, a Gaussian random variable with the same variance as Y, but satisfying this optimal transport property. And this scheme, obviously by construction, will have the same law as the schemes that we defined before. And it will be adapted to the filtration, and we can derive a martingale property for this Ti with respect to the filtration. And this martingale property allows us to derive Ronval arguments. So this is how we construct it. It's a bit abstract way to do it, but it's the one we found for now. Finally, I will talk a little bit on numerical simulations because we did some numerical simulations. So they are not really easy in practice because numerical simulation for strong error can cause some problem. First, we have the lack of exact trajectory solution because even for a Lévy process, even if you take like a geometric Lévy process, you can't even have actually a reference trajectory. Like you can write it as the exponential of another Lévy process, but you cannot write it as an exponential of the same Lévy process. It doesn't work like for Brownian motion. So maybe only on the additive noise case you can tell something, but in every interesting cases, you can't really do anything to get an exact trajectory solution. So the method that is usually used in this case is, okay, you just take your algorithm, you simulate a reference solution where you take the number n of discretization steps as big as possible and epsilon as small as possible, of course, in our case. And then you just compare this reference trajectory between some approximation on a coarser grid. But unfortunately, this is only possible if you have actually an increment of a process. So only for this numerical test, we need to restrict our C to be just multiplicative in X. Because if not, at least I didn't figure out a way to deal with the general case for the numerical test. Some of you have an idea, I'm very interested. And the other problem we have is we have a scheme with 2 parameter increments. And this might be a problem because if you want to test strong error, you need to have the same noise on every trajectory you are constructing. And the thing is here, if you change the epsilon, it actually changes the noise itself. So you can't really like do some simulation with different epsilon and still testing the strong error because it changed the noise. And the thing we did to avoid this is, okay, we just take 1 epsilon that will be fixed for the maximum n that we want. And we know that epsilon has to be smaller than n max at the power -1/2 plus 1/p. And then we never touch about this epsilon and we only change the n. And at least in this way, we are sure to keep the same noise for every trajectory. But in another way, it forbids us to see how the epsilon is involved in this. So the first simulation we made is on a very easy case. We have actually a Lévy process, and we have multiplicative noise with a trigonometric coefficient, cos and sine. And our Lévy measure is some truncated alpha stable. And this one is not even time-inhomogeneous, it's just homogeneous in time. And here we did plot in this figure the different strong error for different values of p. So the blue one is for p equal to 2, the green is for p equal to 4, and then 6, 8, and 10. And then you can clearly see that even in this very easy case, you see a dependence in p in the behavior of the strong error. So it really fits the theoretical rates for L2 and L4. And then, okay, it goes a little bit better for L6, L8, and L10. So I don't know exactly why, but at least you can see that they are all different. Another simulation that we did was trying to see how the lack of integrability in the case of time-inhomogeneous process could affect the convergence rate. So are we able to see this zeta here? And actually, we can see it at least a little bit. So we choose the same kind of equation, but here the Lévy measure is depending on the time with a coefficient beta that might be negative. So we make some kind of singularity in time here. We have some things that will not be in L2, but still in L1. And depending on how integrable it is, we can see that we have different rates of convergence. So the blue one is for beta equal to 0, so it's the homogeneous time homogeneous reference. All of these are for the L2 norm, actually. And you can see that if you lose integrability, you clearly have a loss in the rate of convergence, but still it seems to do a little bit better than the theoretical rates. And I think there is many reasons for this. First, we only choose one specific example, and you can choose many type of example of Lévy measure, of coefficients. And also we cannot do anything with non-multiplicative noise here. So maybe there is some parameters that allows to fit a little bit more the theoretical rate, or maybe not. But yes, that's what we are obtaining for now. And this is for the numerical simulation. So in conclusion, we developed some numerical scheme to approximate time-inhomogeneous jump SDE. We used the Asmussen-Rosinski method to approximate the small jumps. And we have been able to derive some convergence rate in LP strong error using optimal transport technique and using the bounds for the CLT convergence that has been proved by Popkov. So we believe that if we have enough regularity on the coefficient, we could also derive some weak error rates. And this work is still in progress. And it is the reason why I don't have any article to give you for now, because we didn't submit it yet. We are still working on the weak error part, but hopefully it will be done before the end of the year, I hope. And for now, we are working in this theorem that I just give for the conclusion about the weak error. And we believe that if the coefficients are regular enough, if the Lévy measure are dominated by some homogeneous Lévy measure, then we can get something in 1/n plus some contribution in epsilon, which is maybe more interesting than the one in strong error, because it's epsilon and the power 3 minus some constant, which is linked to the structure of the Lévy measure here, which is called the Blumenthal-Gator index. So this is, we almost have the proof for this, but we need to write it properly. And some bibliography here. Okay, I think it's pretty much the time, hopefully.
Yeah, no, thank you.
I hope I wasn't too quick.
Not at all.
Do you have any questions?
Thank you. Is there any question for Paul? They are thanking you. Maybe you don't hear it, but they are clapping. I will do it.
Thank you. Yeah, I'm seeing.
Héctor, quizás habla un poco más fuerte porque aquí al menos no te escuchamos mucho.
Sorry. Is there any question in the room or in the online attendance?
I have another question. In the coupling you made at the level of the Euler scheme already, I think. I mean, on one hand you had the Euler scheme, which would be done with the actual Lévy noise, and on the other hand you took
here maybe
the Gaussian variables. I mean, in the proof, or in the scheme of the proof you gave.
The y variables.
The first step with the forcing coefficients, and then there is another.
Yes.
And then,
yes.
Yeah. So, no, further.
Later, the y variables.
Yes, when you
Uh,
coupling argument.
This one maybe. So y variables.
But
Okay.
yeah, so in constructing a map, maybe before that, yeah. So this, yeah. So the optimal coupling you apply at the level of discretized processes, right?
Yes.
So,
Yes.
Yeah.
Okay.
So my question is, okay, here you needed the regularity assumption because you want to have a density for the true variable which is associated to the true jumps, let's say.
Yes.
The
Exactly.
increment. So my question is, couldn't you build the coupling the other way around in order to just rely on the regularity of the Gaussian variable that is that you are using? I mean, instead of, so you have the optimal transform map, but in the other direction already.
Yeah, it's effectively something we thought about. So the reason why we didn't do this, if I can remember,
maybe it's not the
should do it reversely. Yeah, I can definitely see the point of this. So okay, if you do this, you need to do the same. I think you need to do the same hypothesis on the process itself. So I'm not sure if you gain something by doing this.
Yeah, I'm not sure if the question makes total sense.
No, I think it makes sense. You can do both ways. You could like construct an optimal coupling of the process with respect to a scheme that you have. But in this case, I think it was a little bit more difficult to do like this because the scheme is discrete and the process is continuous. So
yeah, but I was thinking because when you do the coupling, you do it between discrete processes and discrete time processes.
Yeah, that's true. That's true. But then if you so we do it between discrete process, but the scheme will stay discrete anyway. If you do in the reverse way, then you have to define your whole process xt only based on some discrete parts. And this, I'm not exactly sure how to deal with this. Maybe that's the reason we didn't do the reverse.
Okay, but I thought that maybe you should need that only for this part, not because you already control the frozen.
It's like
you see,
it's like you still want to be able to define a version of the scheme, but I don't know if you can really. Okay, but maybe there is a way to do like this. I'm not entirely sure, so I don't want to say mistakes. Okay. Maybe you're actually right. I need to think about it more. Thank you for the question. It's very...
Okay. Okay, well, thank you very much for
I see your point.
Very, very nice work. And say hello to me from I'm fucking late. Probably yes. Okay. So nice to meet you.
Yeah, sure. Nice to meet you too.
Yeah, thank you very much.
Is there more question in the audience? No? I have a little one in that case. You talk a lot about the 1/p rate in the convergence. Is there other results in the literature for similar problems with the same kind of depending on p rate or
yes, there is actually. If you only take Euler scheme for Lévy process, there is a dependence in p. I think there is one work that shows that if your Lévy noise is only additive, then you have no dependence in p. It has been proven by Dariotis, I think, very recently. But the techniques used are very, very different. And in the case of multiplicative noise, yeah, I think it's not that it's dependent on p. Even if you take only a Poisson process, it will depend on p.
Perfect. Thank you, Paul. Well, if there isn't any other questions, I think we can thanks, Paul, again for his nice.
Yeah,
nice
I have there is. Yeah, I just wanted to ask Paul if you know a result. I mean, based on the coupling between the Gaussian, the increments based on random motion and increments based on the whatever variables. Do you know if there is an application to quantifying the, let's say, central limit theorem for in the diffusive approximation of a jump process of a, let's say, a Markov chain, which is something we were wondering with Hector a couple of years ago, you know, because because typically the central limit theorem results for, let's say, a Markov process converging to, I mean, you know that a Markov process will converge to a ordinary equation, but if you rescale, you do the Gaussian scaling, you know that it converges to an SDE driven by a So, but it's always, I mean, all the proofs available is with convergence. So at some point, Hector, we were wondering if one could do a coupling argument for that. One would exactly, but I guess that was before 2018. So, so probably there wasn't the result by Bob.
Okay, I was also very interested about this problem, especially like to extend this in a continuous version of the scheme. So I found something that if you take the central limit theorem for martingales, even continuous martingales, you have such approximation, but only for the W1 distance, because it's easier to deal with. And for WP, I didn't find anything since that. Maybe I was searching like some months ago. But yeah, it's the only result I know is for the martingale CLT. You can get something for Wasserstein 1 distance. But for Markov process or diffusions in general, I don't really know. Result.
Okay. Okay, thank you very much.
Yeah, only. Maybe for Lévy process with there is a work of Marcus Rice, I think, that gives something like this, but it does not allow to have more complex coefficients as we have here. But maybe you can check out this one from Marcus Rice. I could send you the link eventually.
Okay. Okay. Yes. Thank you.
Okay. Is there any other question? Joaquin? No. Well, in that case, we thanks Paul again for his talk, and we close the recording at least.
Thank you very much.